the following presentation, I would like to talk about a work we had conducted here at Johnson Matthey using a Dynochem modeling tool to manage the heat accumulation at production scale of exothermic chemical reactions. The outline of my work, I will give a brief introduction of my company and the project. Then we will talk about the importance of energy balance on the larger scale reactor and talk about the thermal hazard associated with non-dose control exothermic reactions. And we will describe how we can use Dynochem to try to fit the QR data we collected from reaction calorimetry, be able to allow to us to construct a heat accumulation model on Dynochem. And by utilizing this heat accumulation model, we can verify at production scale the actual heat accumulation. And we do this by verification the model on the RC1 data. Johnson Matthey is a globally present leading player in the CDMO field to serve pharmaceutical company around the globe. We have capability to doing process research development in the lab. We also have a kilo lab, can scale up to multi-kilo quantity of API and a key intermediate. Finally, we have a GMP compliant manufacturing suite, which has been served a lot of leading pharmaceutical companies around the world. As we can predict, accumulation can be varied based on the feed rate and the temperature. The worst case scenario in our mind is in the feed batch is when we lose the temperature control at the maximum level of accumulation. Therefore, we would like to keep the level of accumulation less than 25% if it's possible. With that accumulation model, we would like to verify it. Therefore, we run a reaction in the larger scale in the RC1 at 30 degrees with feed time of 180 minutes. By collecting the TR data from the RC1, we can impose that TR data into the accumulation model to calculate the maximum level of accumulation. As shown here, I'm showing here the QR curve constructed by the Dynochem model, and also the red curve is the QR curve obtained from RC1. For the maximum level of accumulation at equivalent point, Dynochem for the model is in good agreement with actual accumulation measured by RC1. Therefore, we think the accumulation model can give us a satisfactory prediction at even a larger reactor. By taking this to our larger reactor at the manufacturing site, we can simulate the process based on the range of the feed temperature and feed time that they would like to perform, and therefore we can calculate the maximum level of accumulation. In this case, we assume the reactor has a TJ minimum of 0 degrees and a slow response of the jacket temperature controller to be conservative. As I said earlier, the model we choose, we can build a 3D service diagram based on the feed time and solution temperature, which is showing here. This can allow the chemist and the engineer to look at what's the level of the maximum accumulation at different level of temperature and feed time and choose the condition they want to conduct. This model assumes it's a continuous feed of the hydrogen peroxide. And the fast feed rate, you can see from the curve, faster feed rate below 25 degrees will cause higher temperature, higher accumulation greater than 25%. The model will allow us to optimize the feed time and the feed temperature and the temperature based on the accumulation that we want to achieve, and also allow the engineer to look at each of the case so they can avoid the maximum solution temperature below greater than 35 degrees C, which is currently is for GMP purpose. In summary, the Dynochem, the EasyMax heat flow data will be able to fit well greater than 95% in the simplified Dynochem model we presented. And the heat accumulation model will be able to extend it from the QR model, and it's verified by the RC1 data. The heat ubiquity, also the Dynochem UA utility model allow us to estimate the U value, which is in agree with actual value obtained from regression method. We believe and we think this model will be able to allow us to optimize or to minimize the heat accumulation model based on the feed time and temperature, so that we can achieve efficiency and safety. The benefit is that this model will allow us to run the chemistry on the computer without actually doing the lab work, and really save a lot of material, time, and still give us satisfactory result.